Assalamualaikum warahmatullahi wabarakatuh. I'm Anissa Raditya Nurrohmah, one of the author of this paper, and this paper title is Synthesis and Characterization of NMC622 Cathode Material Modified by Various Cheap and Abundant Transition Metal. So let's get started. As we know, energy demand was increased year by year. Energy is a crucial aspect for human civilization. The use of fossil fuel vehicles has begun to be replaced with more efficient and environmentally friendly electrical cars. Energy storage in the form of electronic devices is needed to be efficient, lightweight, not oversized, and has high performance along with its growth. Lithium-ion battery are one of the solutions. Lithium-ion battery consists of four main parts, that is cathode, anode, separator, and electrolyte. Cathode plays an important role in lithium-ion battery. Lithium cobalt oxide is the first layer structure cathode that has been produced commercially, but it is expensive, toxic, and explosive in critical conditions. There are materials that potential to be developed. It's NMC. It's cheaper, higher capacity, good thermal and current stability. Recently, work on lithium-ion batteries has concentrated mainly on rising energy density, and there is no reduction in life cycle and safety concern. That is caused by the structural instability of the anode and cathode chemical compounds. The instability of the active ingredient can cause thermal runaway cell battery. One of the solutions that can prevent from the problem is with atomic doping. Atomic doping is widely used process to stabilize the cathode's chemical structure. High bond dissociation energy offers a better structural stability than it inhibits oxygen release, which is an unavoidable procedure. Primary doping occurs through the substitution of NMC metals by other elements, one of the goals being to reduce cobalt content due to some cobalt weakness, such as politically and economically unstable production countries, as well as high prices. The second part is materials. There is a primary materials that nickel sulfate, manganese sulfate, cobalt sulfate, and lithium hydroxide, and doping materials such as ferrosulfate, titanium oxide, zinc sulfate, cerium oxide, carbon sulfate, and magnesium oxide, and additional ingredients such as ammonia acylating agent and oxalic acid as a precipitant. And the third part is experimental methods. We have four parts in this experimental method. The first is synthesis of NMC precursor, where we mix all of the primary materials such as nickel sulfate, manganese sulfate, and cobalt sulfate with a molar ratio of 1 molar equals to 6 to 2 and mix into aqueous. We add the ammonia solution as highlighting agent and then agitate for 2 hours. After that, the slurry was filtered and the precipitate was washed many times until the pH was neutral. And the second process is synthesis of metal doped oxalate. It's using co-precipitation of the metals doping with oxalic acid solution. The third process is synthesis of NMC cathode. The NMC precursor was blended and combined with the lithium hydroxide with 5% excess from NMC moles and the doping materials, using a porcelain mortar and pestle. After that, the mixture was calcium for 6 hours at 480 degrees Celsius and sintered for 12 hours of 800 degrees Celsius in a furnace with flowing of oxygen. The fourth is characterization method. We use SEM, XRD, and FTIR. SEM is used for morphology of the material, XRD for crystal structure, and FTIR for the functional group. After we get the characterized material, we need to fabricate the battery. The first process is mixing the active material with conductive agent like AB, and binder PVDF using a solution that is NMP. After that, we coat in the aluminum foil and thread in the vacuum oven. So we can press with the rolling machine and do the fabrication of cylindrical battery and do the electrochemical performance test. This is the last part, that is result and the discussion. We have four results, that is XRD, FTIR, STEM, and electrochemical performance. The first is XRD. We have the result of XRD of NMC622 with various doping. The first is iron, titanium, and zinc. From each molar or composition, we choose the best composition using the calculated characterization performance, that is lattice parameter and air coefficient. From iron doping, we have 5%, titanium 1%, and zinc 1%. And the second is XRD cathode NMC622 with doping of cerium, cuprum, and magnesium. Same as previous, we choose the best composition of each metal. For cerium, we got the best of 5%, cuprum of 5%, and magnesium 5%. And the second is FTIR result. This is the third figure that shows of FTIR spectra of precursor A and cathode material in B graphic. From the A graph, we can see the precursor have a functional group of water and carbon-oxygen bond. And after the process of sintering, the bond is lost. So the free presence of water molecules and carbon-oxygen bonds disappear or lost after calcination and sintering process. And the second is SAM. It is the SAM of NMC622 image with various doping using magnification of 5000. From this image, we can see that secondary particles appear on this image. And the second is with the magnification of 10,000 times, and we can know the primary particle from this size. And this is the ADX SAM of the one of the sample, that is NMC with iron doping, and it can be seen that from the ADX text, the iron doping was successfully being doped in the NMC. And this is the size of the NMC with various doping. NMC622 without doping has a primary particle size in the range of 1.35 and 8.7 micrometers. That is larger than the NMC with doping. And the fourth is electrochemical performance, and figure 6 shows that the charge discharge test NMC622 using various doping. And from this graph can be seen that the best NMC doping is sourced by NMC with cerium doping and NMC without doping. And this is the cycle test of NMC 622 using J doping and NMC 622 without doping. The decrease in capacity of NMC 622 without doping after 4 cycles was 88.7%, moderate with doping cerium, the decrease in capacity after 4 cycles was higher, that is 96.63%. So it can be seen that using doping we can stable first capacity. And the other result is a reduction in cobalt amount for the production. On the basis of the same amount of material, the use of doping will also reduce the number of cobalt needs. This is the conclusion. The effect of the doping composition of transition metal in NMC622 cathode material is different for each metal. NMC622 cathode material with transition metal doping has almost the same crystal structure characteristic as NMC622 cathode material without doping, but the morphology and particle size is different from NMC622 material without doping. In electrochemical tests, NMC622 with cerium doping has almost the same capacity as NMC622 without doping, with the same synthesis process, and has better initial cycle stability compared to NMC622 without doping. This paper is supported by Indonesia Endowment Fund for Education through Pendanaan Riset Inovatif Produk Invitasi Grant number PRG 6 LPDP 2020. This paper is also supported by PT Pertamina. Thank you. That's all our presentation about our research. Wassalamualaikum warahmatullahi wabarakatuh.